EEE 145, Chapter 12, Line Protection, Part 2. All right, this time we're going to go over transmission line protection compared to last time, which was distribution line protection. So again, we should always ask, what is the purpose of the device we're trying to protect? So what is the purpose of transmission lines? To transfer energy from the generation side to the distribution grid. Right, so it's kind of medium in between the two. Now remember, this is a very high voltage level. A lot of energy is being tossed around in the transmission system. So with that being said, it's vitally important to keep it online as much as possible. You ever hear of system-wide blackouts? That's typically caused on the transmission system. Something goes wrong in the transmission system and it blacks out half of the country. Okay, so some of the philosophies that we need to run by is any permanent fault that happens should be cleared ASAP. So we need to clear these faults as fast as possible. And this is for protecting the equipment. So we don't want transmission lines to burn down. Those things are about $10 million each. Okay, it depends how long it is, high voltage, but minimum, I'd say a good medium is $10 million. Don't want to lose that. So protection of equipment. So maybe protecting equipment. And equally as important is to keep the system online. Keep the system on. Okay. If we have a fault on the system, that fault is going to collapse the power grid as a whole. And if it stays online too long, we're going to overload the transmission lines nearby, feed in energy into the fault. Generation units will probably start tripping offline because they're getting overloaded too much. And then we'll have a cascading blackout that could take out half of America if we're not careful. So again, any permanent faults need to be cleared as soon as possible. Next thing is, for these faults, the minimum amount of breakers are tripped to clear the faults. Okay. Tripped to clear the fault. The system is automatically designed to take a hit or two and stay alive, because we always have to think Murphy's Law, where something's going to go wrong. Even two things will go wrong. So if something goes wrong, naturally, we want to disturb the system as least as possible when that disturbance happens. So when a fault happens, only trip the minimum breakers to just take that one section of the fault out. Don't take extra lines out or a couple of substations for one fault, because you could destabilize the whole entire power grid. So minimum breakers are tripped to clear the fault. And if possible, any overhead transmission lines should be re-energized. Oops. Re-energized ASAP. Okay. So transmission lines are very vital to sending power. If we lose too many transmission lines, we're going to have to start shedding load on the system, or the system might become unstable. So if we have a fault, if it's temporary, or a transmission line locked out when it shouldn't have, because we had to miss coordination, we need to re-energize that transmission line ASAP to try to stabilize the system. So I'm going to even say, help stabilize the system. Okay. Now, protection should not restrict recovering from a power swing. If you have heard of a power swing in the power system, is when you have a big amount of energy from one side of the power system going to another, and that's a swinging effect. Okay, so you'll have a surge of energy kind of parse through the entire power system. Now, the surge of energy will cause high amount of current And some of the relays could misdiagnose it as a fault. So anytime a protection system sees a power swing, we need to make sure we let it recover. So should not restrict cover of power swing. And this means not tripping lines out. Okay. And remember this, there is no fault involved. Obviously, if there's a fault, you need to trip offline. But in a power swing, it's typically just generators fighting each other or a sudden loss of load somewhere. You're going to have this kind of imbalance for a few seconds. We don't want the protection system to jump in and then falsely flag it as a fault and trip transmission lines offline. Because when you have a power swing, you're already at a very dangerous part in the power system. Any power swing can lead to a blackout if not controlled. So let the power swing happen, let it stabilize itself. But if we come in and start tripping lines out, we're just helping the power swing go out of control even worse. And I'll be honest, a lot of the most recent power blackouts in the last like 20, 30 years have been, a lot of them have been in the fault of the protection engineers. We programmed relays, they acted when they shouldn't have and helped create a blackout. So we've, as a protection engineers, we've been under a lot of scrutiny to make sure this should not happen anymore. That's why I'm harping on it so much, okay? So it's it's a very strong amount of responsibility for doing transmission level protection, because if you cause a blackout, it's all on you. 100%, not 100%, but a large portion of it is going to be on you, and you're going to have to redesign the system, explain your reasonings, and the worst thing will happen is if you're a protection engineer, you're in charge of high voltage transmission line protection, and you do it wrong because you don't understand what's going on, and then you cause a blackout for all of California. If you keep your job, I'll be surprised, to be honest. Right? So not trying to scare you, but I'm just trying to show the importance of transmission line protection. It's pretty high stakes. Okay. So please pay attention. Please do your research when you do this type of protection settings. I mean, and to be honest, it's typically left to the senior level protection engineers. New protection engineers typically aren't given this as a sole responsibility, but you will eventually be that senior engineer. So the earlier you learn it, the more you can see the other protection engineers do it, and the more you can learn and quicker you could get up to become that senior engineer, and eventually you will be responsible for your section of the power grid. Okay, so here, let's talk about transmission line coordination. Remember, transmission lines are loop systems that have many lines connected. So think of it as a giant mesh grid, or think of it like a spider web where lots of lines all come together in different nodes. So we need to make sure that when we coordinate line protection for our lines, we're paying attention to the lines, our neighboring lines, and other areas that we could affect if we program it incorrectly, or we can act as a backup for our neighbors as well. So it's kind of like a mesh level of protection systems on top of each other to protect the whole power grid. Now, there are 3 methods we can use for transmission line protections. Number 1 is your 87L relay or a line differential. I'm going to put a star by this because this is everybody's favorite right now. Everybody loves this. And if you have a choice, line differential will always be the best. Second best, which has been used for a while, is the 21 relay. This is a distance protection. This uses impedance-based relaying with their zone 1, zone 2, zone 3s. It's acceptable. We've been using this for 100 years. There's pros and cons to it, but it's up there with differential protection. These are the 2 main ones we use. An older version is 67, which is a directional overcurrent relay. Current protection. This has been used for quite a while, but this is kind of not good anymore, because a lot of those blackouts and miscoordinations, most of the time has been because of the 67 element. Sometimes the 27, but definitely the 67 has caused a lot of issues in the past. 87 line differential is a relatively new technology. It's only been out for like 30 years or so, 20 or 30 years. So 87L has taken the crown as the #1 best, while 21 relays are #2 best, and we kind of crossed out 67 directional overcurrent protection. Their books still teach this, but in my opinion, it's not even worth touching this in today's world. Almost no one uses directional overcurrent protection, and if they do, it's for very, very specific reasons, and you can look up any details you need. So kind of Ray said, let's go to again, which of these instantaneous protections, which of these are instantaneous protection that typically serve as primary protection? Remember, any differential is considered instantaneous. So 87 line differential is going to be our primary protection. Remember, one of the key factors is we want to trip as fast as possible, and there is nothing faster than differential protection. It's pretty much everybody's favorite. What's an impedance relay that typically serves as backup protection to line differential is your 21 distance protection. Okay, and honestly, the 87L and 21, those are kind of side by side. You'll see them in almost every transmission level protection scheme. Okay, let's go ahead and do the line differential first. So here, let's talk about designing it. Now, the differential scheme, you already know this from chapter 6, but we're just going to apply it to a line rather than a transformer or a generator or the other devices we've seen. So first off, label the differential zones. How do we create borders with a differential protections? It's where you locate the CTs. You should always put the CTs on the other side of the breaker. You always want to wrap the breaker into our zone. Our zone will consist of the line and the circuit breakers right here. Okay. You could technically put it on the other side of the circuit breaker, but there's no reason why you wouldn't put the circuit breaker inside your zone just to have an added layer of protection. So at bus A, at substation A, we'll have an 87L relay looking to the CT, and then on substation B, we'll have an 87 relay as well there. So you're going to always need 2 relays at one at each substations for transmission line protection. Okay. So I'm going to write, just remember, wrap the circuit breaker into the zone as well. Okay. Now, if the CTs and relays are so far apart, how can we calculate the current difference? Because remember, between substation A and B, this could be 50 miles apart. We can't just run hard wire for 50 miles easily. The voltage drop across 50 miles of copper wire is going to be too much. Luckily, in today's world, we have better communication schemes than just telephone wire that we've used. The biggest one is fiber. So we use some level of communication scheme. The communication is required between substation. And one of the reasons why 87L differential relays were relatively new only in the last 20 or 30 years is because the communication system has matured only in the last 20 or 30 years. In the 1960s, we did not have line differential protection because in the 1960s, we did not have fiber optic communications. We did not have Ethernet. We did not have high-speed internet. And so this line differential was impossible back in the day. So here, let's talk about what's the extra equipment needed. Well, each 87 relay will have to talk to some type of fiber modem. Okay, so you can have some type of networking gear is needed. AKA a modem, to transfer energy from the 87 relay to the fiber optic modem, and then you'll have a fiber optic path to the other line. So you physically run a 50-mile fiber optic bundle on the transmission line, and then you'll have another modem at substation B, and they'll talk to each other through that fiber cable. And then that 87L will relay information back and forth. So you can see the fiber modem is literally just a medium to send information back and forth. So in the purely protection world, once you connect two relays by fiber optics or other communication means, they might as well be at the same point now. The 87L is substation A can talk to the 87 substation B in less than 1 millisecond lag. They might as well just be right next to each other electrically, which is good because then they could talk to each other easily. Okay, so we had to install some networking gear at the substations. We also need that communication medium. So we'd have to literally install 40, 30 miles of fiber optic cable on the transmission line towers with the main cable itself. And that could be pretty expensive. So differential protection is quite an expensive feature or an expensive protection package, but again, it's one of the best. So this is how you would design a line differential. So 2 relays, 2 CTs, sets, and then modems and fiber optic cables in between. Okay. Now, let's go ahead and talk about what would happen if we have low current or fault current and flowing through the line differential. So let's kind of analyze how would line differential operate. So if we have a line differential set for line AB, we assume 200 amps of low current flowing from A to B. So we have 200 amps flowing into the line from A and 200 amps flowing into the line out the line to bus B. This is a pass-through current that our transmission line is sending out from A to B. If we have our 87L at substation A, how much current will it sense on the line? So with the CT and the 87L relay, it will sense 200 amps is flowing into the line. And at substation B, the other relay there will notice that there's 200 amps out the line, flowing outside its zone. For differential relaying, what's that calculation that it always does? It takes the difference of the current, the delta I, which is I in minus I out, which is, in this case, 200 minus 200. That's equal to 0. So because the current coming in is the same as the current going out, aka node analysis, we don't have to trip, right? Remember the whole idea of node analysis or Kirchhoff's current law is all currents entering a device must also exit at some point. So the transmission line, if 200 amps enters a transmission line at one point, it must exit out another point, which is bus B. Okay. Now, what happens if we have external fault? Right. So remember, this is our zone. If we have a fault outside our zone at bus B, should we trip? Well, it's outside our zone, so I could say, no, we should not trip. So let's analyze how does this differential know that even though we have high current, it's outside our zone. So let's say we have 3,000 amps flowing into our line, which is fault current level. We get 3,000 amps flowing outside our zone, which is fault current level. Okay. Because it's out our zone, we should not trip ever on the differential protection. Another type of protection might trip, but it's not going to be the differential one, right? Because differential is 100%, it's in our zone, we trip immediately. If it's outside zone, we 100% ignore it, even if it'll kill us. It's a hard rule, okay? So let's do the analysis again. If I have a bus A, my A7 relay is going to sense 3,000 amps into the line because that current is entering to my zone. Bus B will see 3,000 amps leaving or going out of the line, which is my zone. So again, let's do our analysis. What's the difference in the current flowing in? Well, I in minus I out is going to be equal to 3 kiloamps flowing in minus 3 kiloamps flowing out, again, is equal to 0. So we should not, no trip. Okay, which makes sense because we're outside our zone. Remember, it's back to that current law. If I have 3,000 amps flowing into my zone and nothing's wrong with my line, it needs to exit somewhere else, which is where bus B is, because the fault is pulling the 3,000 amps into the fault. Okay. Now let's talk about an internal fault, right? So here, so this should be, sorry, a internal fault. Okay. So if we have a fault internal, which is right here, fault, we're going to have 2,000 amps flowing in from bus A. And then we're going to have 2,000 amps flowing in from the other side from bus B. Because remember, in a transmission line, both sides of the line can be a source. So we can have a voltage source here. We can have a voltage source here. We can have two generators on both sides of our line a little farther out. So when a fault happens, current will flow both from both sides of the line into the fault. So we're feeding from both ends. So how is this differential relay going to operate? Well, first off, from the relay at bus A is going to see 2,000 amps into the line, which is normal, right? So I see 2,000 amps coming in. I expect 2,000 amps flowing out on the other side. Sorry, that's a 2, not 3. But I don't. I see 2,000 amps flowing in as well. So I see another 2,000 amps into the line, which is weird because I expect it to be going out. So 2,000 amps going into the line is actually negative 2,000 amps flowing out of the line, right? Because remember, normal Kirchhoff's current law, if I see the 2,000 amps flowing into bus A, I want to see 2,000 amps flowing out of bus B, but I don't. I see 2,000 flowing in. So I can reverse the current arrow and say I have negative 2,000 coming out, which is needed because when we do we do the difference, or we take the difference in the current, it's going to be I in minus I out, right? So I in on one side is 2,000 amps, 2 kiloamps. I out is actually negative 2,000 because we're actually flowing into the line. And then we add this, when we take a negative is a positive. So we actually have 4,000 kiloamps as a differential current. And then this is a huge deal. This is a fault detected. So the relay is smart enough to know internal fault detected, which is equal to a trip, right? And that's how, again, that's how the differential relay will know if a fault is internal, both currents are going to be flowing in. Kirchhoff's current law will not be obeyed anymore. We're violating it. And now we should trip because something's obviously wrong. Okay, so that's how line differentials work. It's just like any other differential protection, except we're just specifically looking at a transmission line. Okay, so now that we understand the basics and how it operates, let's start talking about designing it. What are the things we need to figure out to design to then construct it? Well, the first thing is we know we have an 87 relay on both ends. So we need an 87 relay at bus A. We also need an 87 relay at bus B. So anytime you do line differentials, you know you must purchase two separate relays. Now, we need to have a set of CTs coming into the line. We need to have a set of CTs on the other side of the line. So at a minimum, we're going to need two sets of CTs. Okay. And remember, these CTs have a CT ratio, CTR. You need to figure out what the CTR is going to be. So if you remember how to do CT ratio designations, remember we select the CTR to have 5 amps secondary current. Secondary flowing into the relay under normal loading. So you need to know, what is my typical load current flowing through this transmission line? Is it 500 amps, 600 amps, 200 amps? Whatever that load current is, pick the correct CT ratio to make sure you have up to 5 amps secondary flowing into the relay. Okay. For the minimum pickup for line differential, and I'm going to highlight line differential, okay, because this is separate from our typical overcurrent differential. I mean, overcurrent pickups. The pickup for a line differential, which for a SEL relay is, I believe, 87 OP for operating current. So this, this is a setting name. This needs to be 50% of full load amps. Now, this is not a typo. I know we use 150% for overcurrent pickup for the longest time, but this is not overcurrent. This is line differential, so totally different type of relay operating at totally different type of protection principles. So our rule of thumb is take half of the full load amps. That's going to be your pickup. Okay. And make sure it's higher than the charging current. Charging line current. Okay. So whenever you when a transmission line is dead and you're re-energizing it, there's going to be inrush of current just to energize the line. You need to make sure your differential pickup is above that. Otherwise, it's going to trip immediately when you try to energize your line. Okay, so just remember, 50% of full load amps, higher than your line charging current. That should be more than enough for the differential relay to operate for any type of fault you'll see. Okay. So why don't we go ahead and take a 15, 20-minute break, do a line differential design example, kind of follow suit what we had before. So go ahead and draw your CTs where they should be. Don't forget to wrap your circuit breakers, draw your pair of 87 relays, draw any communications equipment and mediums that should be installed with the relay. Calculate your CT ratios for all CTs on both sides of the line. Calculate the minimum pickup value, which we talked about previously. Okay. And then, oh, one thing maybe I should remind is, remember the minimum pickup value, this is in secondary amps. So you will have to go through your CT ratio to figure out that current. And, you know, this pickup current should be like a few amps, not like 100 or 200 amps, okay? So just don't forget, you have to go from the CT ratio, you have to go through CT ratio to the actual secondary current the relay sees. Then the second page for this example is, again, I like to check our settings. Let's say we have a line fault in the middle. We have 1,000 amps flowing from bus A, 1,500 amps flowing from bus B. Let's go ahead and calculate our secondary current that the A7L is going to see in bus A. Calculate the secondary currents on bus B that A7L will see. And let's actually calculate that line differential current, or the differential current between the two relays. Okay. And we'll go ahead and remember, this is going to be in secondary amps, because you calculated secondary currents from the first two bullet points. And then we'll compare it to a minimum pickup, which you defined on the previous page, and should we trip or not. Okay. So again, it's just a good way to double check your work to make sure that your numbers are safe. So let's go ahead and take that 15, 20-minute break. We'll come back and we'll check your answers. So I'll see you then. All right, welcome back. Let's go ahead and check this line differential design example we left off on. So first things first is, you have a bus A, bus B, you have a line in the middle. Draw where the CT's A7 relays communication channel should be installed. Remember, we want to put a relay at the edge of the lines, include the circuit breaker within our zone. So it's called wrapping the circuit breaker for added protection for the circuit breaker itself. A7L relay should go on each substation, so you need 2 of those. The CT should be attached to them so you can sense the current on the line. For the A7Ls to talk to each other, we're going to have a fiber channel in between. So you're going to have 2 fiber modems on both sides, and then you're going to have some communication medium in between, so you're going to have to run fiber lines between the substations. So that's all the hardware you're going to have to install. Calculate the CT ratios for both CTs, because they're on the same line, the load current is 200 amps for the line. They're going to be the same CT ratio. So you have low current of 200, you want a secondary relay current of 5 amps. So then naturally just you do a 200 to 5 CT ratio to match low current to the 5 amp secondary of the relay. Next, we have 87 operating minimum pickup. So remember, the rule is 50% of full load amps, but this is in secondary current, so you have to divide by the CT ratio. So you can have 0.5 or 50% times 200, divided by 40, so you'll have 2.5 amps. That is your 87 operating value. This is your minimum pickup for the differential relay. And again, this is just a setting, and at least the SCL relays, you're going to have to calculate and program every time. So let's go ahead and do a quick check on your design settings to make sure that it'll operate. So you have a fault inside the line. You have 1,000 amps flowing in from bus A. You have a 1,500 amps flowing from bus B. It's very common for these currents not to be exactly the same because your system will not be perfectly balanced whenever you have a fault. So you might have more generation on one side and less on another. So don't be too shocked if the currents are different coming in from both lines. So let's look at bus A. We're going to ask how much secondary current is flown into the 87L relay. So it has 1,000 amps primary, it goes to the CT ratio. You have 25 amps flown into the 87L at bus A. At bus B, you have an 87L, you're going to do the same thing. Because you're going into the line now, it's going to be negative 1,500 amps divided by 40 for your CT ratio. You get negative 37.5 amps. Take the difference of these two, you're going to get 62.5 amps is your differential current. And then you got the relay will check, is my differential current greater than my 87 operating pickup current? Yes, by a huge margin. So then this is a very strong, easy decision for the relay to trip and take the line out of service, which it should, because it's a fault. The line is faulted, it's draining the system, so we need to disconnect this line so the system can recover. Okay. So with that being said, the differential the differential protection is basically the best of the best right now. Use that. But again, in protection business, we always have to have a backup plan. So this is where we can do distance protection, the 21 relay, as a backup to the differential relay that we use. So going here, let's go ahead and just do a quick review of zone protection because we've already seen it before. So we're going to have the 21 relay right here at substation G, and it's going to be looking in to line GH. Okay. So just to recall, zone 1 is always 80% of the primary line you're looking at with a 0 cycle delay, right? This will go to G1. And so we could kind of do a little visual aid. So our zone of protection is about right here. Okay, next we'll have zone 2, which is 100% of the primary line plus 20% of secondary line. This is about 20 cycles. This is going to go to G2. It kind of looks a little funny. G2 shows 50% of the line, but it really should be 20%. So that's going to cover both our side and 20% of the next. That's a little too thick. Let's make it a little thinner. It could fit easier. Yeah, that should be good enough. Okay. There you go. All right. And then zone 3 will be 100% of first line plus 100% of second line. And this is that 50 cycle delay. And this should go to G3 point. Okay, so again, make sure a little smaller. Can go from our relay all the way past zone 1, past zone 2. It's going to be 2 substations away. And that's our 200% zone. So again, remember 3 zones, zone 1, zone 2, zone 3, right? And each one has a longer cycle delay to let the other relays act faster. So zone 3 is our last line of defense. We should let everything else operate first. So that's for one relay. Let's go ahead and analyze what would happen if we have a fault, how many relays would operate, and what's a backup of which relay is a backup of which other relay in zone protection. So remember, when you have a fault in any line on the transmission side, both ends of the line will have current. So the question is, in a transmission system, fault current can come from which directions? Both ends of the line. So definitely expect it to happen. The line. So that being said, we're going to have a relay at substation G and a relay at substation H, both of them looking into the line. So we're going to have a 21 relay here. We're going to have a 21 relay here. And they're both looking into the line this way and this way. Okay. So if we have a fault midline, which relays will serve as primary protection? So the 21 relays at G and H, their zone 1 and zone 2 will be primary protection. So here we have our 21 relay at G. This is our zone of protection right here, both zone 1 and zone 2. Okay. And that should cover 100% of the line. Okay, so this is our primary zone of protection right here by these relays. Okay. Now, what will be a backup in case either one of these fail? It'll be a zone 2 or a zone 3 from the next substation. So the next substation. So next substation's 21 relay, zone 2 and 3. Okay, so for here, we would say, let's use that. It'll be this zone right here. So this is either zone 2 or zone 3 from this relay right here. Okay. That is a backup to our line GH. On the other hand side, the zone GH will be protected from the left-hand side by some relay over here at another substation. Okay, it doesn't draw all the way out there, but there should be another substation on the left-hand side. That relays zone 2 or 3 should look into our substation. Okay, so general rule of thumb is, or our line, primary protection is done by the relays at our ends of the substations. Backup protection is done by our neighboring substations looking into us, helping us out. Okay, and with every transmission line having a 21 relay, we can actually layer all their zones across an entire power system to where everybody backs everybody up, at least one substation over. So this is that blanket or layer or protection that we put on the transmission system to make absolutely sure any fault happens, we should have multiple layers to prevent any damage from occurring. Okay. If you do end up damaging its device and the transmission system, it's a very bad thing. Burning down the transmission line is huge because they take about 10 to 20 years to build. So if we lose a high voltage transmission line for the next 10 years, we're going to have to be running in some type of contingency mode or some type of backup emergency mode for the power grid. Something's going to happen while we try to rebuild it. So I've never heard of a transmission line ever burning up in my lifetime. I've heard of a tornado taking down a substation for the high voltage system, and that was really bad. And that took several years to rebuild. So this is a big deal when this type of stuff happens. And if we could prevent it by having layers of protections, we absolutely should. So summing it all up, what are the best practices for transmission line coordination? Standard practice in North America, primary protection will always be 87L. That's a preferred method line differential. Backup protecting should be 21 distance protection. And a third layer should be a 21 relay at next substation looking in. Some people are actually even talking about, instead of having backup 21 relay, people even say putting a second line differential. That has its pros and cons, but just traditionally, every utility I've seen, A7L for primary, 21 for backups, and then the next substation over is another 21 looking over. Now, we have 3 layers from different relay types. We could go a next level and double each one of these at a specific substations. So I could say, let's do 2 times the 87L at our substation. Okay, meaning not only are we going to have one actual relay, we're going to have 2 sets of relays, both looking at differential. So we'll have like primary protection squared. Okay. Now it's a very common practice in North America to where we'll even mix the manufacturers just to make sure we're more resistant to cybersecurity attacks. So for an example, for double primary protection on a high voltage transmission line, I will use SEL 311L, which is a line differential by SEL. The communication protocol will be fiber optics. And then a second line differential will be overlapped with a GEL90, which is a General Electric differential relay. It's good to use different manufacturers in case we have a cybersecurity attack that affects every SEL relay in the system. And if the SEL relay fails, our GE relay will still pick everything up. So that way, a cyber attacker can't just target one manufacturer and take it all out. And if we'll even go to the next level, we could use a different communication protocol or medium in case our fiber optics get cut. We could use something called power line carrier. Okay. There's just another type of communications, or you can use wireless or radio or microwave, anything that's not fiber. That way, not only do we have 3 levels of relay type of protections, we also have on top of 3 layers, each layer can be doubled up with different manufacturers and different mediums. So if you do it right, you can actually get up to 6 layers of protections: primary squared, backup squared, third layer squared, if you really want to mix and match all of your relays and manufacturers. Some utilities do this, some don't. It really depends on, can your employees handle different types of relays, or are they too stubborn? They don't want to learn GEs and other relays. So that's up to you and your boss. But if you're talking about what's the best solution, it's always a mix and match manufacturers for relay protection. So with this insanely robust system, can we anywhere in our power protection plan, can we find a single point failure? The answer is no. Always double covered. Right? We're double covered by different relay philosophies, either using A7L or 21. We're also double covered by different manufacturers. We're also double covered by different communication protocols if needed. Okay. So that's all I have for transmission line protection. I hope you guys learned a lot. You're gonna hopefully use this in your career. It's gonna be an exciting 20-year career if you become a transmission protection engineer. And with that being said, I think we'll call it a day for now. We'll come back next week, figure something else out. And you guys have a good day. Catch you later.